In this video, we're going to talk about how to evaluate limits algebraically. Assume that we're trying to evaluate the limit as x goes to c of f of x, where c is a real number. We often don't use a graphing approach to evaluate a limit. Rather, we can use an algebraic approach if we remember the following steps. First, if the curve is continuous at x equals c, then we simply evaluate f of c. Okay? So for instance, in the video that some of you might have seen earlier, we were evaluating the limit shown. Well, we could have recognized that that is a continuous function over all real numbers, and so it's continuous where x is equal to 3 on both sides of that. And we could have just subbed in an x value of 3. If you recall, that was the one where the parabola look like this, and the 0.34 was on the function, and a lot of you might have said, well, obviously the limit as we approach from the left and the limit as we approach from the right will both be equal to 4. And that's what this first rule is saying. If it's a continuous function at that value, just plug it in. Okay? Now, sometimes though direct substitution leads to a result of 0 over 0. That result is undefined. However, the limit might still exist because there could be a hole there. This also occurred in another question we had where we ended up having to evaluate the limit shown, where I've circled part of it. And what we recognized was that that curve is actually just x plus 1, but x cannot equal 2, so there's a hole there. And what we recognized was, you know what, as we approach from the right or as we approach from the left, we get the same value, and the limit is just equal to the y-coordinate of the hole. Okay? And that happened. Well, actually, that's a rule. So when you get an indeterminate form of 0 over 0, you can try the following. Factor numerator and denominator, and the offending factor might cancel out of both. So for instance, in the example I just showed, we had x plus 2 times x plus 1 over x plus 2, and the limit was being requested as x approached negative 2. Well, we could have just factored, as I've done here, crossed these out, and said, you know what? We're going to have a curve with a hole at the point negative 2, negative 1. So the limit as x goes to negative 2 will simply equal negative 1. And we could have just done that. It's a little sloppy what you see on your screen, but a lot of you might have sort of intuitively said that. You might have said, listen, it's just the y-coordinate of the hole. I can tell just by looking. That's another rule. Now, sometimes we're going to learn something about called rationalizing numerators and denominators, and that might lead you to be able to directly substitute. We might be able to simplify a function prior to substituting to see if that allows you to directly substitute, maybe cancel out. And sometimes we're going to introduce a new factor that allows numerator and denominator to become a difference or sum of nth powers, and then that'll sometimes create the offending factor, allowing it to be crossed out in numerator and denominator. So they get a little more complicated as we go, but basically what you see here is a lot of situations with step 2 in front of you where we have holes and we're looking for the y-coordinates of them. So in summary, to evaluate a limit algebraically, try the following. 1, if the curve's continuous at x equals c, evaluate it. 2, if direct substitution leads to 0 over 0, the limit perhaps doesn't exist, but we don't know yet. Try the following. First, factor numerator and denominator, see if we can cross out the factor. Second, rationalize numerator and or denominator. We'll get to that when we get to it. Third, simplify the function. Sometimes it's pretty straightforward math that allows you to do what you need to do. And fourth, introduce a new factor that allows numerator or denominator to become a difference of nth powers. And you'll see what we mean when we get there. So examples where direct substitution leads to the correct answer. Suppose we asked you to evaluate the limit as x goes to 5 of x squared plus 2x plus 3. Well, this right here is a continuous function. So we're simply going to plug in an x value of 5, and the answer is 32. Okay, that's the answer. The limit as x goes to 5 of x squared plus 2x plus 3 equals 32. Okay, next one. What if we have the limit as x goes to 5 of 11? Well, the function y equals 11 is continuous over all real numbers, and so the limit as x goes to 5 of 11 is simply 11. If it helps you, think of it this way. The function y equals 11 is shown in red. It obviously has the point 511 on it. As we approach an x value of 5 from the left or an x value of 5 from the right, our y value is going to 11 rather obviously. Okay. So since we get the same result from both sides, we get the answer of 11. Okay, and sometimes imagining the limit being evaluated graphically can help you to evaluate a limit algebraically. It's always good to have multiple tools in your toolkit. Now, what if we want to evaluate the limit as x goes to 0 of x minus 1 over x plus 1? This might look like a tough question at first, but it's really not, because the function has a discontinuity at x equals -1. Granted, there's a vertical asymptote there, but it's not discontinuous at x equals 0. It's got continuity on both sides. So as long as the curve is not discontinuous at the x value in question or in the neighborhood around the x value, we can sub in the x value and solve. Now you might say, well, how big's a neighborhood? And the answer is as small as you want it to be. As long as there's any amount of continuity on one or both sides of the x value in question, we can actually evaluate that limit algebraically. So in this particular question, we are discontinuous at an x value of -1, but on both sides of 0, we're perfectly fine. That's not a problem. And at 0, we're continuous, so we just plug in an x value of 0, and we end up with a limit equal to -1. Now, this next one, sometimes people look at this and they say, oh my gosh, you know, this is going to involve some complicated math. It actually doesn't, because it's designed to be a little bit tricky. It looks complicated, but the denominator actually doesn't equal 0 when you plug in an x value of 3. In other words, plugging in an x value of 3 actually doesn't cause any problems here. So just sub it in and evaluate. So when you sub in an x value of 3, you ultimately end up with √2 minus 2 over -√6. We can multiply top and bottom by -√6. And we end up with -2√3 plus 2√6 over 6. We can factor 2 out of the top and the bottom, and we end up with -√3 plus √6 over 3, or in other words, √6 minus √3 all over 3. And that's the answer. Now, let's talk about some examples where direct substitution leads to 0 over 0, but you can factor and divide out the offending factors and sub in the relevant x value. Now, when I say divide out the offending factors, I mean cross out. So what if we wanted to evaluate this limit here? Well, subbing in an x value of 3 results in 0 over 0. So that's a problem. So we don't give up, though. We're going to factor. So if we factor, the top is already factored, the denominator actually becomes x plus 4 times x minus 3. We can actually cross out these x minus 3's right there, and we have the limit as x goes to 3 of 1 over x plus 4. Now we have changed this into something where we can simply sub the 3 straight in. And note that after we sub in the x value of 3, there's no more x's in the expression. There will be no more need for the limit notation on the left. But you have to keep putting it in for the time being. So what I mean by that is this. We still have x's here, so we still need the limit notation here. Okay, but now I'm going to take this x value of 3, I'm going to plug it straight in. Now there's no more x's, so there's no more need for the limit notation. And we evaluate 1 over 3 plus 4, and it equals 1 over 7. So really what's going on here is we have a curve that looks something like this. And it's got a vertical asymptote. It's got a hole at the point 3,1/7, and all we're saying is that the limit as x goes to 3 is equal to 1/7, and we can see graphically that that's the truth, because as we approach from both sides, the one-sided limit from both sides is 1/7. Okay. Now, what if we wanted to evaluate what you see here? Subbing in an h value of 0 is going to create the indeterminate form of 0 over 0. So one thing we can do is expand the numerator. So simply expand out 2 plus h quantity cubed. And when you do all that and collect like terms, you get the numerator shown here. Okay. Now, we still have 0 over 0 if we sub in an h value of 0, but now we can factor. Okay, this is what we had at the on the last page, that line right there. Common factor out an h from the numerator, and we'll be able to cross it out with the h in the denominator. And when we plug in an h value of 0, we get an answer of 12. So what we can say is the limit as h goes to 0 of 2 plus h quantity cubed minus 8 over h is equal to 12. Okay? Now another method is a little bit quicker. Hopefully you can see that what you've got there is a difference of cubes. If you let w simply equal 2 plus h, then what you've actually got in the numerator is w cubed minus 8, and in the denominator you've got h. So let's factor w cubed minus h. You get, again, recognizing it as a difference of cubes, w cubed minus 2 cubed. We end up with w minus 2 times w squared plus 2w plus 4. Now what we can do is sub in a 2 plus h for w. So w minus 2 becomes 2 plus h minus 2. And we still have w squared plus 2w plus 4. We can now, this 2 plus h minus 2 is actually the same as just h. So we have a factor of h in the numerator. And of course, we still have that factor of h in the denominator, and we can now cross them out. Okay? And so what we've actually got is the limit as h goes to 0 of w squared plus 2w plus 4. Remember that w is the same as 2 plus h. So subbing in that, we can have this expression right here. And we can certainly now plug in an h value of 0 when not have any problems. Doing that, we end up with the answer of 12. So the limit as h goes to 0 of 2 plus h quantity cubed minus 8 all over h is actually equal to 12. Now, what if we have the limit as x goes to negative 2 of x to the 4 minus 16 over x plus 2? This is another situation where we're just going to have a hole, and we're going to come up with the y-coordinate of that hole, believe it or not. So subbing in an x value of negative 2 gives 0 over 0, because negative 2 quantity to the 4 minus 16 over negative 2 plus 2 is equal to 16 minus 16 over negative 2 plus 2 is 0. We get 0 over 0. So our first thing to try is to just plug it straight in and see if it works, but it doesn't work. So we're going to try factoring. Okay? And we might see here that what we can do is use a difference of squares up top. We get x squared minus 4, x squared plus 4. And then we see that we can actually factor out x squared minus 4 to x minus 2, x plus 2. And we still have the x squared plus 4, and we have the x plus 2. We've got a factor of x plus 2 on the top and the bottom. So we actually can now say we've got the limit as x goes to negative 2 of x minus 2 over x squared plus 4. Plugging in an x value of negative 2, we can say we've got negative 4 times 8 ultimately, which is negative 32. So we can say that the answer, the limit as x goes to negative 2 of x to the 4 minus 16 over x plus 2 is negative 32. Something I'd like to point out is that when we got the 0 over 0, and we got it by evaluating a limit as x goes to negative 2, something to look out for is the vast majority of the time what we're going to end up doing is finding a factor of x minus negative 2 on the top and the bottom and crossing it out. So if we're determining a limit as x goes to negative 2 and subbing in gives us the expression 0 over 0, then what we want to do is get a factor of x plus 2 and the top and bottom cross it out. If we're determining a limit as x goes to 3 and we get of some expression and we get a 0 over 0 indeterminate form when we plug in the 3's, then chances are what you want to do is get a factor of x minus 3 at the top and the bottom, cross them out, and then figure it out that way. So oftentimes I'll call that the offending factor, and in most cases you can tell what it's going to be at the start of the question. Okay, now what if we have the limit as x goes to 25 of x minus 25 over root x minus 5? Well, if we sub in an x value of 25, we get the indeterminate form of 0 over 0. So let's try factoring or another method. In this case, we could try factoring, but it's important right now to discuss that we could rationalize the denominator instead. So we'll discuss that technique later in the show, in the slideshow. Now, you might be saying to yourself, wait a second, how can we factor? X minus 25 is unfactorable, but this case is going to be considered different. And you might say, well, what would, reading the last sentence, why would we think about factoring here when the previous training we've had tells us not to? And the answer is because you have 0 over 0 as a result. You have to try something. And the numerator is a higher degree than the denominator, so maybe we can factor the numerator and cross out like factors. So now we really scratch our heads. We say, how the heck could we factor that if we had to? And right now you might recognize, well, it's kind of a difference of squares actually. It's like root x minus 5 and then root x plus 5. And, you know, you can try that because you got to try something. And so you try that, you make the numerator root x minus 5, root x plus 5. You recognize you've got root x minus 5 underneath. You can cross out those factors. And so now you've got the limit as x goes to 25 of the root of x plus 5. You can just sub 25 straight in. Notice that for as long as we've got x's in our expression, we're still using the limit notation. So now what we do is we plug a 25 in for x. So we've got root 25 plus 5. That's 5 plus 5, and that's 10. That's our answer. Now what if we have the limit as x goes to 2 of x squared minus 4 over x cubed minus 8? Plugging in an x value of 2 will give us 2 squared minus 4 over 2 cubed minus 8. That's 4 minus 4 over 8 minus 8, which is 0 over 0. So right away we see, okay, we've got the indeterminate form of 0 over 0. So let's try factoring. We see the top is a difference of squares, the bottom's a difference of cubes. Okay, so factoring the top and the bottom, we end up with the limit as x goes to 2 of x plus 2 over x squared plus 2x plus 4. We get that after crossing out our x minus 2's. Okay, and we had... we're not really surprised that we crossed out x minus 2 factor on the numerator and denominator because we were determining a limit as x goes to 2 and plugging in gave us 0 over 0. So we have the limit as x goes to 2 of this expression right here, and we simply plug in a 2 and we end up with 4 over 12, which simplifies to 1 over 3. So the limit as x goes to 2 of x squared minus 4 over x cubed minus 8 is 1/3. Now, let's look at something a little bit different. This is going to get interesting here. If n is a positive integer, then a to the n minus b to the n equals a minus b times a to the n minus 1 plus a to the n minus 2b plus a to the n minus 3b squared, etc., all the way down to ab to the n minus 2 plus b to the n minus 1. So, for instance, suppose n was equal to 2. The first factor will be a minus b. The second factor, n is 2, so the second factor will be a to the 2 minus 1, which is a, and then down on the end, b to the 2 minus 1, which is b. Okay, and all of these other terms are unnecessary because there's n is only equal to 2. What if instead n was equal to 3? Well, then our first factor will be a minus b. And our second factor would be, again, think of it that a is equal to 3. We're going to have a to the 3 minus 1, which is a squared. And then we're going to have a to the 3 minus 2 times b, which is the same as a to the 1 times b, which is ab. And then we're going to go down to the end. All of these become unnecessary. And we go down to the end and we have b to the n minus 1. Again, n in this case is 3. B to the 3 minus 1 is the same as b squared. So if we were to follow this thinking all the way through, if we were to determine if we had a to the 5 minus b to the 5, we could simply say we start with an a minus b because we have a difference of nth powers. Both of the powers there are to the same exponent, and it's a positive integer. So we have a minus b. And then our second term, we're going to have a to the 4. It's always 1, whatever this, if that's a to the 5, reduce that by 1, so it becomes a to the 4. And then put a b to the 4 on the end, okay? And then in between, every term is just going to be, since this is has a 4, the next term will be a to the 3, b to the 1. The next one is a to the 2, b to the 2. The next one is a to the 1, b to the 3, and then finally b to the 4. For instance, with a to the 6 minus b to the 6, we have the same exponent on each power. It's a difference, so we say our first factor will be a minus b. Our second factor, we'll just subtract 1 from 6, and we'll have a to the 5. On the end, we'll have a b to the 5. And then in between, we're just going to have every term necessary, subtracting 1 from the exponent on a and adding 1 to the exponent on b until we get to the last term. So starting with a to the 5, we then have a to the 4, b to the 1, a to the 3, b to the 2, a to the 2, b to the 3, a to the 1, b to the 4, and finally b to the 5. Okay? Now, it also works when n is odd, and there's pretty good reason for that, but this works for the sum of nth powers. So the sum of nth powers factoring works when n is an odd positive integer. And it's a very similar formula. One way to remember it is this. What we learned in the last on the last slide was that a cubed minus b cubed is a minus b, and then a squared minus a squared plus ab plus b squared. And so now what we're going to do, we're going to change this to a plus, and then our second factor will alternate minus and plus. So we'll change that to a minus, and we'll leave that as a plus. Similarly, on the last slide, we learned that a to the 5 minus b to the 5 would be a minus b, and then a to the 4 plus a cubed b plus a squared b squared plus ab cubed plus b to the 4. Okay, well, what we're saying now is if you have an odd positive integer, in this case 5, then change that first one here, that minus there, or sorry, the minus that's right there, change that to a plus. And now in this next bracket, you have 4 pluses. Instead of 4 pluses, make it minus plus minus plus. And that'll work. That'll give you what you need. If you expand that out, if you expand out a plus b times the second factor of a to the 4 minus a cubed b plus a squared b squared minus ab cubed plus b to the 4, you will actually get, after simplifying it, a to the 5 minus b to the 5. It's something that always works. But the sum of nth powers factoring only works when n is odd. Difference of nth powers factoring works for any positive integer. Okay? So the rationale why it works that way can also be shown below. I'll give you, you can screenshot that if you want. And so now back to our lesson on limits. What we've done here is we've shown you a new way of factoring, because that new way of factoring might come in handy for some of these harder questions. So suppose we were given the question to determine the limit as x goes to 3 of 2x to the 4 minus 162 over negative x to the 5 plus 243. Our instincts are telling us we probably want to get an x minus 3 in the numerator and in the denominator so we can cross it out, because we're determining a limit as x goes to 3. So what we're going to do first is common factor. In the numerator, we common factor out a 2. In the denominator, we common factor out a negative 1. And what we recognize now is we now have a factor in the numerator that's a difference of fourths, because what we have is in the numerator a factor of x to the 4 minus 3 to the 4. And in the denominator, we have a factor of x to the 5 minus 3 to the 5. So our numerator is going to give us an opportunity to use difference of fourth powers. Our denominator will give us an opportunity to use difference of fifth powers. Okay? And that's what's shown here. So using difference of fourth powers in the numerator, we have x minus 3. We now have x cubed plus x squared 3 to the 1 plus x to the 1 3 to the 2 plus 3 to the 3. Using difference of fifth powers downstairs, we have x minus 3. And then we have x to the 4 plus x to the 3 3 to the 1 plus x to the 2 3 to the 2 plus x to the 1 3 to the 3 plus 3 to the 4. Okay? So what we can then do, and it's shown here, is we have a complicated factor. Granted, this one right here is fairly complicated, and this one right here is even a little bit more complicated, but they're both factors, as are this x minus 3 right here and that x minus 3 right there. Well, they're factors, so we can cross them out. We've crossed out that offending factor. So now in the next line, what we can do is plug a 3 directly in for all these x's in the numerator and all those x's in the denominator and simply evaluate. Okay, plug in that 3 for all the x's in the numerator or in the denominator. All right, and we have no more need for the limit notation because we'll have no more x's after we do that. So we show it one more step here. We actually show with our x minus 3's have now been canceled from top and bottom, so they're gone. We don't have to show that, but we're showing it here. And now, like I said, we just take that 3 and we plug it in everywhere we see an x. Okay, and that's what's happening in the next line. Now, when you do that, you're going to end up with, in the numerator, we still have that factor of 2, as well as 3 cubed plus 3 squared 3 plus 3 squared plus 3 cubed. In the denominator, we still have that factor of -1, as well as 3 to the 4 plus 3 cubed 3 plus 3 squared plus 3 cubed plus 3 to the 4. Ultimately, what happens is our numerator is 2 times 27 plus 27 plus 27 plus 27. Our denominator is -1 times 81 plus 81 plus 81 plus 81 plus 81. And we ultimately get 216 over -405, which is the same as -8 over 15. So believe it or not, if we were to actually graph that function right there, what we would have would be a function that's continuous on either side of x equals 3, but there'd be a hole at 3, -8/15. And all we're really doing, believe it or not, is an elaborate finding of the y-coordinate of the hole. Let's look at our next question. X is going to -2, and we have the rational function shown there. Well, if we let x equal -2, -2 to the quantity to the 7 will be -128. We'll have -128 plus 128 over 10 times -2 plus 20. We'll actually end up with 0 over 0. So when we see that, again, we tell ourselves, let's get to work. So we need to factor. We can't common factor the numerator, but we can common factor the denominator, and we can use the sum of 7th powers factoring on the numerator. So we see instead of x to the 7 plus 128, we might think of that numerator as x to the 7 plus 2 to the 7. So we then have a plus b, which is x plus 2. And then in the second factor, we have a to the 6 minus a to the 5b plus a to the 4b squared minus a to the 3b cubed plus a squared b to the 4 minus a b to the 5 plus b to the 6. But we're plugging in instead of a, x, and we're plugging in instead of b, 2. So what we end up with is, believe it or not, a factor of x plus 2 in the numerator, a factor of x plus 2 in the denominator. We can cross those out. Our offending factor is gone. Now, we don't necessarily have to show this next step, but we're going to just clean it up a little bit. We still have x's in the numerator, so we're still showing our limit notation. And now, what we're going to, and we're also showing our equal signs here. It's important in a question like this, we're also showing where all our equal signs are, putting them in the right spot. So now what we're going to do is we're going to plug in -2's, and we end up top with a whole bunch of 64's added together. The top ends up actually being 448, the bottom is 10, and that's equal to 224 over 5. Now, sometimes we'll have direct substitution lead to 0 over 0, but we can rationalize the numerator and or the denominator, then perhaps factor, then cancel, then substitute. So suppose we have the limit as h goes to 0 of root 16 plus h minus 4 over h. Now, directly substituting in an h value of 0 leads to the indeterminate form of 0 over 0. We can't factor. However, when we have a binomial with the square root like we do in this case, we can often multiply numerator and denominator by the conjugate of that binomial. So to determine the conjugate of a binomial, we leave both terms the same and change the operator between the terms from plus to minus or minus to plus. And what this does is creates a difference of squares and often has the desired effect of allowing us to evaluate the limit. So the conjugate of root 16 plus h minus 4 is root 16 plus h plus 4. We literally just change the sign in between. So what we're going to do is we're going to multiply the top by root 16 plus h plus 4. This is going to create a difference of squares up there that'll be to our advantage. But you all know that if you multiply the top of a fraction by something, you have to multiply the bottom of the fraction by the same thing. So we'll make sure that we do that. We're going to multiply the expression by that. Okay? So what we now have is root 16 plus h minus 4 times root 16 plus h plus 4 up top. Now watch what happens. Root 16 plus h times root 16 plus h is 16 plus h. We're then going to add 4 of these root 16 plus h's, and we're going to subtract 4 of those root 16 plus h's. Okay, and then finally we're going to subtract 16. And what will happen if we do this correctly is this middle piece right here is going to cancel out. And so what we're going to be left with is 16 plus h minus 16, and we all know that that's just the same as h. We're going to get a factor of h up top. Okay, so let's show our work here. The square root of 16 plus h quantity squared is the same as 16 plus h. That middle part cancel out like they do in a difference of squares situation. We're not going to expand that denominator. You might ask why not, and the answer is because our problem is we get values of 0 in the numerator and denominator. So we're going to leave the h alone as a distinct factor of the denominator because we're trying to generate h as a factor of the numerator so we can cancel them out. So in other words, having a factor of h right here is exactly what we want. So don't expand it into the other factor. Okay, so up top we end up with 16 plus h minus 16 because again these pieces here canceled out. That's the same as h. The numerator is the same as h. And so now we've got the limit as h goes to 0 of h over h times the factor underlined right there. These factors of h cancel out. Our numerator is now 1. We can show this step if we want. We've got the limit as h goes to 0 of 1 over the square root of 16 plus h plus 4. Now, we still have h's in our expression, so we still have limit as h goes to 0 showing. But now we can take that h value of 0 and we can plug it in. And so our denominator is now root 16 plus 4. So it's our overall fraction is 1 over 4 plus 4, which is 1 over 8. So the limit as h goes to 0 of the root of 16 plus h minus 4 over h is actually equal to 1/8. What if we have the example shown? Well, subbing in an x value of 2 will directly lead to the indeterminate form of 0 over 0. So what we're going to do is we're going to multiply top and bottom by the conjugate of this expression. Now, what's the conjugate of root 27 minus x minus 5? And the answer is root 27 minus x plus 5. So we're going to multiply top and bottom by root 27 minus x plus 5. Okay, and see where that leads us. So we show that there. Now, we can put them together as you see. The square root of 27 minus x times the square root of 27 minus x is 27 minus x. We then have positive 5 root 27 minus x, negative 5 root 27 minus x. They cancel out. Negative 5 times positive 5 is negative 25. And so what we end up with is negative x plus 2 underneath. Okay? And we're showing a couple of steps where we show how we're going to get that negative x plus 2. We're not going to distribute the top because we like the fact that there's an x minus 2 up there because we kind of have an inkling that's what we want to cross out. So we've got a factor of x minus 2 up top and a factor of negative x plus 2 down below. We then can common factor the numerator and actually the denominator in this case. So we see factoring out that the denominator was negative x plus 2. We're going to factor out that negative 1. And when we do that, we're going to be able to cancel out these x minus 2's. And we're now going to be in a position, we still have x's showing in our expression, so we still have limit as x goes to 2. But now we're going to be able to plug in that 2, and once we do that, there are no more x's, so no more need for the limit notation. And we're going to end up with 10 over negative 1, which is also known as negative 10. Now, this next question is just like the first one, except, just like the two we've done before, except the only thing really different about this is we want to determine the conjugate of the numerator and the denominator. So direct substitution leads to the indeterminate form of 0 over 0. Therefore, we need to multiply the numerator and denominator by the conjugate of the numerator and also by the conjugate of the denominator. Now, the conjugate of the numerator is 3 plus root x plus 1. And the conjugate of the denominator is root 24 minus x plus 4. Therefore, we could multiply numerator and denominator by what you see there. That would totally make sense. And that would make our next step look like what you see at the bottom of the screen. And that totally makes sense. But let's just switch this order down below. There's a reason why I'm saying that. So let's just switch those two. It doesn't matter what order we multiply them in. So we put them, you'll see here, the only difference is that we've just changed the order of those two. Now what we're going to do is we're actually going to multiply these two together. And we're going to multiply these two together. Okay, and we're not even going to worry right now in the next couple steps about those two factors out there. We're still going to keep them with us, but we're not going to do any work with them for the time being. Okay, so expanding everything out, we end up with what you see here. Literally 9 minus the quantity x plus 1, and down below we end up with 24 minus x minus 16. Okay, now expanding that negative sign in, we get 9 minus x minus 1 up top as a factor, and we get 24 minus x minus 16 as a factor down below. We still have these factors here, and we still need to keep them along with us. But if you haven't quite seen why we've done that yet, you'll see in a minute. We don't want to distribute into the last factor in either the numerator or the denominator because we're trying to create the same cancelable factor that would allow us to cancel them both out. Okay, so what ends up happening is this 9 minus x minus 1 is actually the same as 8 minus x. And 24 minus x minus 16 is actually the same as 8 minus x. And so that's what we have. We can actually cancel these two factors out. And we still have x's in our expression, so we're still going to have a limit as x goes to 8. But now we're in a position where we can actually push that 8 in and sub it in for x, and we won't get an undefined value. And so what ends up happening is we get the answer of 4/3. Ultimately, what has happened here is if we were to try and graph y equals 3 minus root x plus 1 over 24 minus x minus 4, what we would end up with is a whole at 8, 4/3. But the function would be continuous on either side of that whole. And so we just basically have just a sophisticated version of us finding the y coordinate of a whole. Okay, and that's actually what the limit is equal to. Now, sometimes we'll have examples where direct substitution leads to 0 over 0, but we can simplify the expression and then directly substitute. So let's look at this question here, 1 over x minus 1 over 2 over x minus 2. This is in some ways easier than the factoring questions because we're going to rely on some grade school skills here. First of all, we see that if we sub in an x value of 2, we'll end up with 1/2 minus 1/2 over 2 minus 2. That's the same as 0 over 0. That's the indeterminate form. We can't have that. So let's just look at the top and say, okay, let's get a common denominator up here. So our common denominator, if we're trying to subtract 1 over x minus 1 over 2, our common denominator is 2x. So we change 1 over x to 2 over 2x, and we change 1 over 2 to x over 2x. And we subtract, we get 2 minus x over 2x, and then all of that is over x minus 2. So we're dividing by x minus 2, so that's like saying we're multiplying by 1 over x minus 2. And so we have ultimately the limit as x goes to 2 of 2 minus x over 2x times x minus 2. Now, we're going to factor -1 from the numerator and then rearrange the terms. So if we factor -1 out of 2 minus x, we end up with -2 plus x. Well, we know -2 plus x is the same as x minus 2. We have a factor of x minus 2 top and bottom. We're actually not surprised by that because we suspected from the start that would probably be our offending factor. And so we can say we've got the limit as x goes to 2 of -1 over 2x. All right, and now we plug in an x value of 2, and we have -1 over 4 as our answer. Now, sometimes we're going to get direct substitution leading to 0 over 0, but we'll be able to create a difference of nth powers or sum of nth powers when n is odd, and then we're going to be able to factor and directly substitute. And some people find it beneficial to introduce a new variable during their solutions to these questions, but it's not necessary. So for instance, what if we wanted to evaluate the limit as x goes to 64 of the cube root of x minus 4 over x minus 64? Okay, direct substitution leads to the cubed root of 64 minus 4 all over 64 minus 4. That's the same as 64 minus 64. That's the same as 4 minus 4 over 64 minus 64, which is the same as 0 over 0. So plugging it in gives us 0 over 0. We're going to have to try a new technique. So a mistake that a lot of people make is they'll say, okay, well, we have square roots. Let's multiply top and bottom by the conjugate of the numerator. And actually, that's wrong. The reason we don't do that here is because it only works if it's a square root sign, that process. The reason is it ultimately leads to a difference of squares. But if it's a cube root sign, we're not interested in creating a difference of squares. We're interested in creating a difference of cubes. So what we're going to do, you'll see here, we would end up with x to the 2/3 minus 16, which wouldn't get us anywhere. It wouldn't allow us to cancel out with the problematic factor of x minus 64. So the lesson we're learning here is multiplying by the conjugate only works for square roots. So instead what we're going to do is not think of a minus b times a plus b equals a squared plus b squared, but think about creating a difference of cubes. So if we're presented with a cube root, we should multiply numerator and denominator by a factor, which allows us to create a difference of cubes, or possibly a sum of cubes in a different scenario. So to refresh your memory, difference of cubes is shown right there. So going back to our solution, we recognize a potential difference of cubes in the numerator, a cube root and a minus sign. So we're going to let a be the cube root of x, and we're going to let b equal 4. And by doing that, what we actually have up top is a minus b. Okay, now we're looking to create a difference of cubes. So we already have the a minus b factor. So now we add in the second factor, which is a squared plus ab plus b squared. And we introduce that to the top and to the bottom. Okay. So now up top we have a minus b times a squared plus ab plus b squared, and on the bottom we have x minus 64 times a squared plus ab plus b squared. And we recognize, hey, that top, that's exactly the same as a cubed minus b cubed. Okay, so we can put that down there. And now what we recall is that a is the cube root of x. So if a is the cube root of x, then a cubed is x. And if b is 4, then b cubed is 64. And so the numerator, instead of thinking of it as a cubed minus b cubed, let's think of it as x minus 64. We've got x minus 64 on the top and the bottom. We cross them out, and we have 1 over a squared plus ab plus b squared. Okay? Now, recall that a is the cube root of x. Well, that's like saying a is x to the 1/3. Same thing. B is 4. Okay? So, a squared, since a is x to the 1/3, a squared must be x to the 2/3. Or, some people prefer to call it cube root of x quantity squared. AB, which is this middle term, that's going to be x to the 1/3 times 4. And b squared is going to be 4 squared, which is 16. Okay, so we can put all that in the denominator. Now, we have x's still in our expression, so that means we still have x's written here, limit as x goes to 64. We plug a 64 in for each of our x's, so there's no more need for the limit notation. We know that the cube root of 64 is 4, so instead of saying the cube root of 64 quantity squared, we can say 4 squared. And instead of saying 4 times the cube root of 64, we can say 4 times 4, and we still have that 16. So our bottom is 16 plus 16 plus 16, which is 1 over 48. And so we can answer the question, the limit as x goes to 64 of the cube root of x minus 4 over x minus 64 is actually equal to 1 over 48. In summary, sometimes you need to evaluate a limit that has a binomial in the numerator and or the denominator. Direct substitution leads to the indeterminate form of 0 over 0. You may be able to create a difference of nth powers or a sum of nth powers, but sum of nth powers only works if n is odd. So for example, if after common factoring, if you have a binomial where one of the terms is a third root and we're subtracting, try creating a difference of cubes. If we have a binomial where one of the terms is a fifth root and we're adding, try creating a sum of fifth powers, etc. Let's try this question. We have the limit as x goes to negative 121 of 3x plus 363 over the fifth root of 2x minus 1 plus 3. If you plug in a negative 121, the numerator and denominator will both equal 0. So we can common factor the numerator. Now, we have a suspicion at the start of this question that we probably want to get a factor of x plus 121 in the numerator and the denominator so we can cancel them out. So we see right away the numerator is going to be 3 times x plus 121. So we're going to get our x plus 121 in the numerator pretty easily. In the denominator, it's going to require some more work. But what we see is we have a fifth root and we're adding. So let's try to create a sum of fifth powers. If we let a be the fifth root of 2x minus 1 and we let b equal 3, then our denominator is actually just a plus b. So what is the second factor of the sum of fifth powers? Well, it's a to the 4 minus a cubed b plus a squared b squared minus ab cubed plus b to the 4. So let's introduce this factor to the bottom. Now, obviously, that'll create our sum of fifth powers, but if we introduce this factor to the bottom, we're going to have to introduce it to the top as well. So we first thing we do is just factor the top. Second thing we do is call this expression a and call this expression b, so our denominator is just a plus b. Then we say to ourselves, we'll let this be the first factor of a sum of fifth powers, so the second factor will be this. We multiply the bottom by that, but now we have to multiply the top by that as well. So we have this expression here. We now recognize on the bottom that that's simply a to the 5 plus b to the 5. That's the whole point of this process. The bottom is now a to the 5 plus b to the 5. Now, a is the fifth root of 2x minus 1, so a to the 5 is 2x minus 1. And b is 3, so b to the 5 is 243. So this bottom is really the same as 2x minus 1 plus 243. Okay. And 2x minus 1 plus 243 is the same as 2x plus 242. And that's the same as 2 times x plus 121. We've actually got the x plus 121 up top and down below. And so we now have this expression right here. We've really gotten to a good place, but now we have to evaluate every one of these terms. And it's not as hard as you might think. But we have to evaluate a to the 4 and a cubed b and a squared b squared and ab cubed and b to the 4. So let's do that. It's not too tough. We remember that a is the same as the fifth root of 2x minus 1, so it's the same as 2x minus 1 to the 1/5, and b is 3. So really a to the 4 is just the fifth root of 2x minus 1, quantity to the 4, and a cubed b is just 3 times the fifth root of 2x minus 1, quantity cubed, etc. B to the 4 is just going to be 81. And so we can plug everything in here, just like that. And now we still have x's in our expression, so we're still carrying the limit notation. Okay, we have all of our equal signs in the right place. Now we're going to take this negative 121 and we're going to plug it in for x. And once we do that, we're going to have no more need for the limit notation. So this second last line is where we've subbed in negative 121 for x. And so what we have is 3 times this large factor, fifth root of negative 242 minus 1, quantity to the 4, minus 3 times fifth root of negative 242 minus 1, quantity to the 3, etc. What we basically have when you plug in those x values is a lot of fifth root of negative 243. Well, negative 3 times negative 3 times negative 3 times negative 3 times negative 3 is negative 243. So in other words, negative 243 to the 1/5 is negative 3. Or as we have written on the page, the fifth root of negative 243 is negative 3. So right here, this fifth root of negative 243, I'm going to call it negative 3 in the next line. This one right here, I'm going to call that negative 3. This one right here, let's call it negative 3. That one right there, let's call it negative 3. Okay, so we plug those in. Now, negative 3 quantity to the 4 is actually going to be a positive number because it's 4 of these negative 3's multiplied, it equals 81. Okay, negative 3 quantity cubed is a negative 27, but remember we're subtracting 3 times it, so it's minus 3 times negative 27. This is going to be positive 9 times 9. This is going to be negative 27 times negative 3, as it says there. And we have 81. What ends up happening is all our terms in that second factor of the numerator are positive 81. Okay? And so we end up with 1215 over 2 as our answer. Now, what if we have a question where we want to create a difference of cubes up top and a difference of squares down below? So in this particular question, if we plug in x equals 56, we get the indeterminate form of 0 over 0. So we're going to create a difference of cubes in the numerator and a difference of squares in the denominator. So we're going to let a be the cubed root of x plus 8, and we're going to let b equal 4. And so we're going to be able to write our expression as the limit as x goes to 56 of a minus b over square root of x minus 40 minus 4. Okay, now we want to create a difference of cubes up top. The reason we want to create that difference of cubes is because we've got a cubed root and a subtraction. Okay, so what's the formula for a difference of cubes? It's a minus b times a squared plus ab plus b squared. That's the formula. So that's why you see what you see right there. But because we're multiplying that by the top, we have to multiply it by the bottom, basic fractions. Okay, but we still need to create the difference of squares in the denominator. Now, most students don't need to use different variables here. They're just going to remember for creating that difference of squares, they're going to multiply top and bottom by the conjugate. Creating a difference of squares is easier than a difference of nth powers or sum of nth powers. Okay, so we're going to multiply top and bottom by the conjugate of root x minus 40 minus 4, which is root x minus 40 plus 4. Alrighty, and now what we're going to do, we're just going to change these two. If we change the order of those two, then we'll have the conjugate times the conjugate, and then we'll create the factor we want and be able to have this piece remaining. And underneath, on top, we'll leave it as it is because that'll allow us to complete the difference of cubes, get the factor we want there, and then we'll remember to multiply by that piece. Okay? So that's what all we've done here is we've just moved things in a more convenient place. So this piece right here, a minus b times a squared plus ab plus b squared, that is equal to a cubed minus b cubed. But we still have this root x minus 40 plus 4, whoops, just like we should, okay? And then underneath this piece right here, root x minus 40 times root x minus 40 is x minus 40. And then we have minus 4 root x minus 40 plus 4 root x minus 40, they cancel, and then we have minus 16. So this piece that I've circled down below, that will ultimately end up equaling x minus 40 minus 16. Okay. We'll get to that later, apparently. So, and actually you can even see it here. X minus 40 minus 16, and these middle pieces will cancel out. And we all know x minus 40 minus 16 is the same as x minus 56. So our inkling that we wanted to create an x minus 56 is already coming true. Now in the numerator, we know that a is the cube root of x plus 8. That means a cubed is x plus 8. So this right here is going to be an x plus 8. And we know b is 4. So minus b cubed is going to be minus 4 cubed, which is minus 64. X plus 8 minus 64 is x minus 56. So underneath, we're going to see the two middle terms cancel out. We're going to have x minus 40 minus 16, which is the same as x minus 56. And so we're actually going to have, hopefully those last couple of slides made sense, but these two things right here each equal x minus 56. So we rewrite our line, leaving the remaining factor in the numerator and the remaining factor in the denominator in place. We've got x minus 56 up top, x minus 56 down below. Our instincts have proven correct. We cancel out the x minus 56's. Okay, and now we just have to evaluate this piece. And we're almost there. So we know that a is the cube root of x plus 8 and b is 4. So a squared is the cube root of x plus 8 quantity squared. ab is 4 times the cube root of x plus 8, and b squared is 16. So we plug those in. And now we still have x's in our expression, so we're still going to carry the limit as x goes to 56 notation. But now in our next line, we plug the 56's in for x. Every one of these x's, we've now plugged in a 56. And what we end up with is root 16 plus 4 over the cube root of 64 squared plus 4 times the cube root of 64. The root of 16 is 4, and the cubed root of 64 is also 4. Okay? So up top we get 4 plus 4, and down below we get 4 squared plus 4 times 4 plus 16. Ultimately 8 over 48, which is the same as 1 over 6.